Okay, good afternoon, everyone. So we have some new faces. So uh, just to make you're also new, right? Yeah. Okay. You're the mechanical engineering student. Yeah. Adam. Okay. Cool. So I'm told you about the stuff you need to do in terms of hardware and stuff like that, right? Okay. That's it. Okay. Okay. So I want to recap and also uh, cannot. I sent an announcement out. Cannot do his office hours today because he made it into finals of some fellowship competition at Qualcomm. So he's making a presentation there. So I'm holding extra office hours after the class. The main thing at this point is I know some students have spoken to me about possible project ideas, but I want everyone else to kind of start doing the same thing. Form teams, that's the other thing. It's a lot more fun to do projects in a team. So start sort of coming and speaking with me. I think um, uh, the best way is for me to know a little bit about what your interests are in terms of applications and all, and then I can suggest some ideas. Otherwise, you can come up with, if you go to Hexaware website, they have links to all sort of places where that platform has been used. So that would be one direction to go with. So what I would do as usual is to start by recapping things that we did last time. So uh, last time we finished Serial IO, uh, and in particular, we looked at UART, we looked at SPI, and we looked at I2C and a bunch of others. And the main thing is that these are techniques by which or protocols via which MCU can talk to peripherals and MCUs can talk to MCU. The two embed can talk to each other, or you can have sensors talking to MCUs and things like that. Very importantly for us, all of these things tend to be available as supported peripherals on most common MCUs, including the one which we have, so that you don't have to deal with a lot of the low-level details. So all the sampling of bits and all are taken care of, and you just get to see as if you are sending and receiving characters. UART is what is used over USB to talk to the terminal on the laptop, as well as to a Python program or any other program for that matter. Depending upon your OS, when you connect your embed or any other device with a UART with cable that converts UART to USB, and then when you connect it, then it appears as a COM port on Windows and as some device under /dev/ something on Unix or Macs. And then you open that device from software, or you run the terminal program, and that way you can kind of interact with it. Then we also talked about GPIOs, which are kind of like the Swiss knife of IOs, and you can indeed implement some of these serial protocols by software-based approaches to using GPIO. And then we talked about analog IO. Uh, the input site is ADC, analog to digital converter, and I mentioned that usually you will have multiple pins sharing an ADC. We also very briefly talked about that uh, you have to meet a certain sampling rate requirement. Uh, does anyone recall what the sampling rate requirement is? If you have an analog signal, how would you sample it? 2 times the highest frequency. And the other way is, if you're sampling at a certain frequency, you have to make sure that the analog signal does not have any frequency above that, because then bad things happen, in particular something called aliasing, and that mucks up the signal basically. But if you meet those requirements, then you can reconstruct the signal using signal processing methods. And then for the analog output side, we had DAC, digital to analog conversion. And here again, you have to feed the DAC at a fast enough pace. But this you cannot share, so you do need to have one DAC per pin, and therefore it tends to be fewer DACs. Okay, so that was a serial IO part, and then we had started looking at how do we uh, develop software, and in particular, we had looked at a few key things. Number one, the development cycle for these differs quite a bit from the way you write software on normal programs, normal computers, in the sense that you are writing a program for a device. So you're going to compile it, perhaps simulate it, then dump it onto the device, test it, and kind of iterate in the process. And I mentioned that how there are a variety of simulators out there. We are not using them, but there is stuff out there, particularly for more popular platforms, smartphones, and then Arduinos and things like that. What we are going to spend time this lecture and in Thursdays to look at now, how do we go around organizing the software on these platforms. So one thing is that since we are dealing with sort of physical signals and all, what's happening on the pins, so you often have to really do programming, which is kind of closer to the hardware. So even if there is an operating system, you will often bypass it, and this is called as the bare metal programming, that you're kind of working directly with the hardware, and that kind of requires both getting familiar with the hardware so that you can exploit capabilities that even if you have an OS, it may not be using, may not be exposing, as well as becoming familiar with what kind of APIs and all are provided. So hopefully by now you have at least visited the os.mbed.org once and kind of looked at uh, kind of APIs and all that they kind of provide out there. Okay. Another concept which has already gone over, but this is this notion of interrupts. This is something that you normally don't see in kind of ordinary programming that you do. You're kind of sitting way above. But at the lowest level of hardware, the way devices talk to the CPU is by doing something to gain their attention. And so, like for example, if a character arrives over a serial port or a GPIO pin sees a, let's say, a rising signal edge, and in your software you are seeking to monitor it. So one approach to do it is this polling approach, where kind of the idea is you spin in the software, periodically checking is the what's the pin level, what's the pin level, what's the pin level, and detect it going up. Or likewise, is there a character for me in the queue? So you kind of repeatedly do that. It's quite wasteful. We cannot put the processor to sleep, for example, and of course we can't do other things. So while polling is something that for quick and dirty kind of checks is okay, but if something is truly asynchronous, that's not a very wise thing to do. So that's where interrupts come into play, where essentially this notion that someone is checking the status of the hardware to see whether it needs attention is now delegated into some sort of a hardware device deep inside the processor. So you can think of it as another specialized processor whose sole job is to monitor all sort of pins and hardware peripherals to see if they need attention. And if they do, then they tell the processor. So that's the concept of interrupts. So what typically in these processors happens is that there might be many sources of interrupts, including some internal ones, like timers, for example, where you can tell a piece of hardware that send an interrupt after a certain specified period of time or periodically at a certain rate. And then most somewhere in the processor would be this interrupt controller, and which is monitoring these different sources of interrupts. And when something of interest happens, it tells the CPU. And the kind of issues that you face are what happens if there are simultaneous interrupts, maybe multiple devices need attention. So typically there would be some sort of a prioritization, which is of the various sources, you will somehow disambiguate order. Which interrupt service routine, ISR, interrupt service routine. Think of it like a function call, except it has to do some additional stuff, which we'll talk about briefly. So which interrupt service routine to call, which would depend upon what the source of the interrupt is. So for example, if it was UART which needed retention, then you call a different function. If it was some GPI open, you need call a different function. So usually somewhere in processor memory area, uh, usually they define a table and where you will put the addresses of the different functions. Uh, so kind of pointer to the function, and then the hardware will go check the address and then call the function or jump to that address. Now, the main thing to which complicates ISRs is the following. Unlike normal functions, in case of normal functions, the compiler knows when and where the function is going to be called from, because somewhere in elsewhere in the piece of code there would be a function call, and therefore compiler can arrange to do things like passing arguments, uh, whatever processor registers state needs to be saved, it can do that so that the interrupt, whatever the function call doesn't interfere with uh, what was happening in the place where it was being called from. What makes interrupts challenging is that they can happen anytime. So while it is possible that a software can disable interrupts if it has the right privileges to do it, but when the interrupt does occur and if the interrupts are enabled, it can happen at any time in the middle of any two arbitrary instructions. And what that means is that uh, there is no way for the compiler to know it, and no way for the operating system to do that. So what would happen is that the interrupt service routine, that function, has to be written in a manner that when it returns, the program which was interrupted doesn't see any change. So whatever register values were there, they should be the way it is, other than kind of skipping some clock cycles, as if the time came to a halt. Nothing else um, should be visible. So it therefore becomes the responsibility of the ISR to save and restore state. And what that means is any register it is going to use and it should save it, perhaps in some area of memory, and then sort of return them back. And the area of memory where you typically save it is the so-called stack, where you push the values and then you pop the values. So ISR need to be compiled differently, because unlike normal functions where compiler uh, follows a protocol and a function knows which registers it can safely use as per that protocol, here there is no such luxury. So any register you want to perturb, you have to you have to make sure that you leave them untouched. Do you think you can pass arguments to an interrupt service routine? Let's say you want to, that whenever the interrupt service routine fires, uh, you want to set behave according to some parameter that you have passed to it. So let's start differently. When we call functions, we pass arguments to it. Like C or C++, we pass arguments to it. How are arguments passed to a function? How does the caller pass arguments to a called function? So you can store them in specific registers, but you can have lots of arguments. So what happens then? Stack. So usually the first one or two arguments would be in registers, and then the remaining are pushed into the stack, and then the called function knows where to look them up. Okay? And stack is kind of like effectively infinite, in the sense lots of memory, so we can kind of keep pushing things. But we can't do that because it's being called at arbitrary places, right? I mean, the interrupt can happen at any place. So how can you pass some data to the ISR? What kind of variable would you use for it? Would it be dynamic? Right. Static. What is static variable? Right. So these are the so-called global variables, right? I mean, which you declare outside any functions. Okay. So in case of embed, you'll write them outside the main, right? So, um, so they sit in an area of memory which is always accessible from anywhere, including by the ISR. So in case of C, when you say static to a global variable, what that means is it's not visible outside that file. Okay, so it has a different meaning. But by just putting it outside the function, outside any function in the global scope, it is static in the sense it's sitting in a global place. So static has kind of a couple of different meanings in that. Okay? Whereas inside a function, what does static mean? So if I write a function, right? I mean, some functions f, and within that I say int x, then x goes onto the stack. If I say static int x, then x goes to global memory. Okay, and but these kind of functions, one has to be careful, because if you make a variable inside the function to be static, that means if uh, two different parts of the program are calling the same function f, they are using the same x there also. So one has to be careful about that. So you can affect the behavior of the ISR by passing it some parameters if you may, but that will have to be through the global variables. Most processors also allow for some hardware flag, some sort of a register, where you can go and check, is there an interrupt forming? So for example, oftentimes you may disable the interrupts and then hold for the thing. So like, let's say instead of the GPIO pin actually causing an interrupt, it will just set an interrupt flag and you will go and check for that. Why might you want to disable interrupts? Okay, so too much interrupt burden, but obviously that interrupt presumably wants to do something. Uh, so uh, what would be kind of a more transient reason for doing it? Yeah, so like for example, in particular, if I'm running a sequence of tasks where I don't want to be disturbed, right? I mean, no additional delays, or I want to make sure that no one else comes and starts using that resource. Okay, so essentially, I want to do it atomically. That's the term, right? So disable interrupt for atomic tasks. Okay, so maybe I'm uh, interacting with some piece of hardware which has some very tight timing requirements or something like that, then I would like do it. Again, all this enabling disable of interrupts and all is not something you can do on a program running uh, on Linux and things like that, because interrupts are an OS level detail, and if you were writing OS modules, then you would be doing it. But when we do embedded programming, essentially the distinction disappears, and you write ISRs as necessary, and you manipulate with these things. So what you see. Yeah, I mean, you could, although it would probably not be a very nice way of programming style-wise, but certainly you could say that, I don't want to be disturbed at all by these sources at that time. But then, and therefore I'll disable it. The only thing is that interrupt disabling, at least in most modern processors, is not a very fine-grained process. You disable everything or you disable everything. So, but Intel processors tend to have a more fine-grained thing, but I think most newer processors work on lower. So what you see out here is the following: that interrupts can come at any arbitrary point in time. Control passes to the ISR. Within the ISR, you will save the state, and then you will, after you do whatever you want, you are going to restore the state, and then you will come back. And all of this is done by the hardware, because this interrupt could have come at any place, and the main program, other than if it were to measure the time here and measure the time here, it will see some passage of time, but other than that, there is no other decision. Some older processors, Intel processors, have instructions which can take hundreds of clock cycles, and in which case they have some very complicated things like if an interrupt comes in the middle of the instruction, they undo the effect of the instruction, handle the interrupt, and then proceed, because otherwise you will not be able to respond to interrupt for a long while. And so those are kind of complicated things. More RISC processors or microcontroller kind of things and all do not have that, so you usually don't have to worry about it. Okay, so what happens in an ISR in interrupt handling is you wait for the instruction to end, other than those weirdo processors I used to push the program counter to the stack so that you know where in the program you were, push all the active registers to the stack, jump to the interrupt handler as decided by the table, and then once you are done, pop the program counter off the stack, and then restart from the place where you left off. Depending upon things, you might want to make your interrupt service routine non-interruptible. So usually what processors do by default is the moment you jump to the ISR, interrupts are disabled so that you do not have nested interrupts. And if you choose to, then you'll have to explicitly enable them, because usually otherwise you can get into some weird kind of chain things. Okay. Final concept when it comes to these embedded systems I want to talk about is that how do we go around organizing different pieces of software sharing a CPU? And I think that's kind of core of what I want to spend time on this slide set and the next slide set. So if you think about what are the different ways we break software into simpler pieces. So the one which we are very, very familiar with are subroutines, right? So function calls, where I'm in one particular function and then somewhere I would say call another function. And then we start at the entry point of that other function, and from the beginning, we process through it, and then somewhere we will return. There could be multiple return points, but we'll return, and then we come back wherever we left off. Okay, and usually processors have some special instructions in support of it. In particular, they'll have some sort of a return instruction, which what it does is it basically takes the address off the stack and jumps back to it. And to make all this magic happen, compilers do additional stuff such as passing of arguments and saving some register state into the stack so that the function call can do things very quickly without burdening itself. But so usually registers are divided into two categories: those which the caller saves and restores, and those which the callee has to save and restore. So we kind of strike a balance, and this is very much compiler dependent. So depending upon what compiler you're using, this calling protocol may differ, but there are some reasonable conventions which are also agreed upon. Okay, so but generally speaking, this is kind of a combination of processor and compiler, both of them kind of coming into play. The other very common way of organizing software into smaller pieces are the so-called threads. How many of you have seen threads in programming? Okay, kind of like some. Okay. So normally when we write a program, it's a single sequential program, right? One instruction follows another instruction, and when we write in programming languages like C or C++, again, there is a single control flow which we follow. And so if there is a function, it starts at the beginning, and then after loops and stuff like that, it exits at some point, and there is some very well defined promise that the programming language makes to you about ordering of the operations, right? I mean, if I say x is equal to 3 and y equal to x, then y will get the value 3, right? I mean, those sequences are very well specified. But what if we want to make things happen in parallel? So in some cases, there are programming languages which have the ability to do parallel things, but more typically is that the operating system provides you the ability to say, create two programs running in parallel. So one very common way we do it is from our terminals, where we can run one program in one terminal, another program in another terminal, and they are running in parallel on our computer. But that's a very heavyweight operation, because because I have to run kind of two applications in parallel. What if you are writing an application and within that application you want to do two things in parallel? For example, maybe you want to interact with two different sources of information, or maybe while you are reading one value from the source sensor, let's say, you want to process the previous value, so you want to pipeline or parallelize. So threads come very useful there. So threads, you can think of it as one or more pieces of sequential tasks, sequential programs, if you may, running inside the same application. Okay, and they conceivably could run entirely in parallel and never interact with each other. And if I have multiple CPUs in my system, then each thread will map to a different physical CPU. But if I have fewer CPUs than the number of independent tasks, then somehow the operating system is very time sharing, right? It will give the CPU for a while to one thread and for a while to another thread, and this process of the operating system deciding which thread to run at any given point in time on a CPU is one of the very key role it does, and it's called scheduling. Okay, so it needs to be scheduled. So this one is hierarchical, sequential, right? At any given point in time, I'm at a single place, one program counter. Here, I am kind of running things in parallel as long as they don't halt each other somehow by sending a message or something. I can basically, at least I have the illusion that as if these two things are happening in parallel. It may be that each one of them is running on a separate CPU within the same system, or it could be that somehow time sharing is taking place and the OS is switching back and forth between these different threads so that I effectively get an illusion of parallelism. So this is sequential, this is simple. Okay? And the other thing you can see is here there is a master-slave kind of relationship, caller callee, and here it's kind of symmetric. These threads are kind of paired to each other. There is a third way software modules get organized, which is less common, or at least less well taught, but does exist, and actually in some emerging programming languages like Go. Anyone heard of Go? So Go is a programming language from Google, which is they're pushing as a replacement for C and C++. And Go uses this abstraction called coroutines. Coroutines are kind of halfway. Okay, so in what manner are they halfway? So before I describe coroutine, one other point I want to mention is in case of subroutine, how many stacks are there? One, right? I mean, all this A was using a stack, and then when I come to B, I'm using the same stack, right? I mean, we just put some additional data into a stack. Whereas in this case, because of threads, each thread has, just like it has its own program counter, it also has its own stack. And that's a heavyweight thing because stacks are memory hungry and all. So what if we could have kind of a symmetric type way of organizing software and yet have a single stack? And that's what coroutines do. So what happens in coroutines is the following. So let's say A and B are two coroutines, and what will happen is that somewhere it will say resume B. Now the difference between resume B and call B is the following. In case of call B, you always enter B at the beginning, at a fixed entry point. What resume B does is it says resume where you last left off B. And likewise, resume A says start in A where you last left off. So I need to remember that somehow, right? Where did we last left off? So first time I do resume B, it starts at the top. But at some later point in time inside B, I say resume A. So in this case, resume A would revert back, jump back to where it left off. Thus far, it sounds like a call. But now later on in A, there's another call to resume B. If it was a function call, I would have again entered B at the beginning. But it's not a function call. Instead, it's a call that will start where I had last exited. So I remember where I last exited and we restart from the same point. And this is very analogous to what happens in threads. In threads, usually most thread APIs will provide something like wait for, okay, some message. So what happens is When you say wait for, the operating system, you kind of exit the thread, so to say, and then when the necessary thing happens, like for example, wait for a signal from another thread, then you will start where you left off. So this is a very important concept, which is restarting where I left off. Okay, threads provided, coroutines provided, and you can go back and forth. So coroutines is the third way. Now, the main thing to remember is we are only at a single place at any given point in time, right? There's a single program counter are either in A or B. It's not as if A and B are both simultaneously progressing. So I only need a single stack. So that's a very important aspect out here. Single stack, and per module stack. Okay, so these are just different ways of organizing software modules and with different properties of concurrency and memory usage and things like that.
So we can say coroutines are not an exact combination of subroutines and threads, but somewhat trying to replicate the best of both.
Kind of, yes. And that they're lighter weight because they use a single stack, and yet the programming style is closer to that of these threads. Another term for coroutines which is often used is called proto-threads. Okay, and I'm mentioning this thing because this way of organizing thing is often kind of people who like the programming style of thread but don't want to pay the penalty, and yet subroutine are kind of way too hierarchical. So that offers kind of a good compromise. Okay, so yeah.
So in the previous, if you have A, which calls resume B,
Mm-hmm.
right, in the coroutines part,
Mm-hmm.
would A still continue to?
No, A stops here.
Okay.
So when A says resume B, I pass the control to the other guy. So I exit. It's like now it's saying resume B is saying resume B and wait for B to resume B back. Okay. So you are at. So that's a very important point. So that you are at any given point in time, you are only at a single place. You have one program counter. Okay, the program counter can be moving back and forth, just like here. Whereas here there are two program counters that are progressing together.
You were mentioning how it's kind of like thread-like programming.
Mhm.
It wouldn't necessarily be thread. It's still similar to subroutine programming. You no longer have to remember, or you can go back and forth between those.
The style of programming becomes one where conceptually you are only worrying about what is happening in my thread. Okay, so I can say things like wait for a signal from the other side. Okay, so when I say wait for, under the hood, control passes to the other side. Okay, because it turns out that a lot of time we use threads in a manner where the thread is waiting for something else. So coroutine naturally works there, right? I mean, if I'm just jumping back and forth between threads, then might as well have a single stack because I'm only in one of them at any given time. So Go takes this thing. So what Go calls as its the threads and goals are basically coroutines. I think it just calls it coroutine. Okay, so so the reason I'm sort of talking about this is that question, a question which comes up in bare metal programming in particular is, and generally all of software is how do you organize the software? And there are kind of really couple of things that are foundational here, and particularly so in embedded systems. Events and concurrency. So by events, I mean that you're writing a piece of software which has to do things in response to things happening around it, right? Signals coming from sensors, GPIO pins, from other pieces of software. And concurrency means that I have to do many things simultaneously. I have to write a piece of software which has to observe this pin and has to look for a character on the UART and has to do some other stuff. There's a whole bunch of stuff naturally happening in parallel. That's that's at the heart of embedded systems in general because they interact with a lot of sensors and all. It's not like a normal a lot of normal programs where you read a file, process it, dump out. Okay, then there's naturally lots of sources of information, and your task often is to kind of like be vigilant for all of them, and whichever occurs in whatever order it occurs, you have to respond to it. Okay, there is no pre-scripted ordering to these events from the outside world. So events and lots of things happening concurrently, or illusion of concurrency. So I want to make a distinction between concurrently and parallelism. Parallelism means you have literally two pieces or more pieces of hardware and they're running. Concurrency means that I am able to do multiple things simultaneously. I'm able to talk on the phone and work on my computer, right? That's an example of concurrency. It's a single me kind of doing it, right? Multitasking. Okay, so must be able to handle events in unknown order at arbitrary times in parallel, right? Illusion of parallelism. And so managing this concurrency is the heart of kind of much of programming at that low level. So this is where those those three programming paradigms I talked about come into play. So um, one way of organizing your software running at that low level is as a bunch of threads. And there would be some sort of, usually we just call it a kernel, think of it like a simple operating system, which provides support for this. And it will provide you APIs so that within the thread, you can make different kind of things. You can ask for a resource, you can send a message to another thread, you can do operations that might require you to wait. So if you go to the embed website, and if you go to the reference documentation and you go under APIs and you go under RTOS, which is real-time operating system, that's kind of the main OS heart of the thing, you would see that it has threads. Okay, and the threads, they are offered, what does it say? It says class that allows defining, creating, and controlling parallel tasks. Okay, so that's kind of the heart of it. The rest of the stuff is for to help the threads with. If you go to threads, it's a complicated looking API. Main thing you would see is there are things to help you create threads, and then start a thread, terminate a thread, set priorities. I will talk about these things. Okay, set the size of the stack, and blah 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 blah. And if we look at an example out here, so yeah, by now hopefully all of you have done at least some embed programs, and typically in these embed programs, what do? We write a main function, and then we do our stuff in it, and then we exit. But what if I want to do two things in parallel? So if you have done a blink LED, now let's say I want to blink two LEDs. Okay, so I could still do it in a single while loop, but now let's imagine that I want to blink one LED at one rate and the other LED at a different rate. So now your while loop will start getting very complicated. So this is the place where separating it out, have one thread handle one LED, the other handle the other LED, and if you have 10 LEDs, then 10 LEDs. So it turns out main itself is a thread. So all we have to do is we have to create a second thread for the other LED. So that's what this guy is doing, which is it starts a thread for LED2. So LED2 thread is something we have defined out here as just a function, except that again, like a thread, it will just continually blink LEDs. So it too has its own while loop, and it is toggling the LED2 and then waiting for 1 second. Whereas in the main loop, we are toggling LED1 and we are waiting for half a second.
Like when you call the thread inside the main function, will it be a slice of, will it be main slice into different threads, or will it be created?
Main will continue, and at this point we have created and started a new thread. Okay.
It's slicing the same thing and giving equal resources.
No. So it's just another data structure got created, and how control goes back and forth between these two. Remember, we have a single processor, right? Is going to be decided by the operating system, right? And in particular, intuitively, what happens is this one of these threads will run. The moment it says wait 0.5, wait is a call to the operating system saying wait for half a second. So now the OS can go ahead and make some progress on one of the other threads, like for example this one. And likewise, this is kind of the control will pass back and forth between the two. So in this system, there are two things going on in parallel: the while loop in the main and the while loop in this thread. Okay. And then this thing provides ways in which you can even pass argument to a thread. So they have another way of doing the same thing, except this time around. So they use a function called blink, which can take an argument, and there is a different style of calling the thread where you can pass an argument to it. Okay. You would see in this case, the example is slightly more elaborate. So in this example, there is also a global variable for running, whose start value is true. And then what happens in the main thread, we start the other thread, and then we wait for 5 seconds, and then we set running equal to false. But since running is a global, it is also visible to this other function. And what this function inside does is, instead of while true, it will do its loop as long as running is true. And the moment running becomes false, this guy also exits. And then finally here we say thread.join, which is basically what this thread.join does is it says wait for the other thread to die. Okay, so essentially when this thread dies, then until then we will keep waiting. So there are a lot of these utility functions to manage this concurrency that's going on. But this is an easy way that we are able to suddenly do things in parallel. In this example, since the time periods were 1, and the previous example that we had, the time periods were 1 and 0.5, you could have imagined doing a single while loop and doing things in alternate iterations. But what if it was some weird number like 1 second in one case and 0.3 seconds in the other? They were not divisible by each other. It would be very messy to do it as a single loop, whereas threads let you separate it out. Okay, so that's the power of thread, that you can focus on one thing at a time and then let them kind of interact with each other. So very useful, but memory hungry, right? Because they now have 2 threads. I need 2 stacks, and how do I know how much stack do I need, and what if there is wastage? So when you are in sort of memory shortage, as we tend to be in these MCUs, threads are kind of a precious resource. So don't use them too liberally, because you can run out. Moreover, here there is no protection. One thread, if it accidentally exceeds its stack quota, it will overwrite the rest, the data elsewhere. So it can be very problematic. Another thing that I wanted to bring out is something that something that would be let's say every sometime t precisely I want to go and read something, let's say from the A to B signal. And when I read the signal, so I want to read it, and then I want to process it. And this, so S equal to read and process S. And this processing can take some amount of time. Let's say this takes some time delta, but delta is less than t. Okay. How would you write this type of a code, where every time t I want to go and read the signal and process it and then read it again? So any suggestion? How would I structure my main? can imagine this occurring very commonly, right? Read functions, everything, process it, and then exactly later. Uh, what are the different ways you can think of doing this? Hmm? Okay, so you've seen enough of embed, so tell me in kind of embed type pseudocode. So I'll have some sort of while loop for sure, right? Because I'm doing it this thing forever. So while true, that would be one way of organizing it. Um, so let's. I'm going to propose something. I'm going to say s equal to read adc. Any comments on this code? Right. I won't be reading because this is additional time. So how would you restructure this code to read precisely? Okay, so that's one approach. So this thing, I can create one thread. All it does is wait t, and then read s, and then wait t. But what if read takes a long time? Then that is a problem, right? This is time. Wait for t is timer, right? I mean, wait for t is saying start the timer and come back after the timer finishes. So this is embed way of doing the timer. It's reasonably accurate and reasonably low. So remember, I mean, we are kind of making an assumption out here that all of this stuff has to be much less than t, right? It takes time, but it's less than t still. So really, the trick out here is one way I can do it is I can do it in this order, right? Wait t. I'm sorry. No, that won't work. Okay, so approach one, two threads. Thread one is doing, so this is a suggestion for you guys. While true, actually, I'm going to combine the suggestion from here and the suggestion from there, right? So what we'll do is we are going to start a timer. Okay. Okay. So I'll chop this thing off. I'll say start timer, and here I will say wait for timer. And the way I would do this thing is in start timer, I would, so you'll have to check whether Embed has an API for it or whether you have to use the hardware directly. But start timer, you are going to do something so that an interrupt comes. And then in the interrupt handler, we are going to arrange that it will read the value. Sorry, it will generate an event, and you're going to wait for this event out here. Okay, so you arrange for the timer to generate a signal for you, and you're kind of going to wait for it. That's the pattern that you'll have to somehow make it happen, so that the timer runs in parallel with the code as opposed to sequence. So that's one approach. But let's say I don't want to go through all this mess, right? Let's say you haven't learned how to. There's an alternative you can think of. So the other alternative you can do is you can read time. Okay, so you can say t equal to read time. Okay, and then you say s equal to read ADC, process s, I'll call this t1, then I'll say t2 equal to read time, and then I say wait for t minus t2 minus t1. Okay, so I kind of apply a correction for it. So there are different ways you can kind of do it. Just think about it, and they obviously have different kind of accuracies. And, issue. We also haven't sort of quite worried about how to calculate whatever time this while true takes. That's also an instruction. So depending upon how precise you want to be, you may have to structure it again. I bring this up because even something as simple as generating a periodic waveform, you have to worry about these things because otherwise a tiny error can build up over time, okay, and can take you way off. So do think about what the temporal properties of these different things could be. Going back out here, so I could have threads doing these independent things. An alternative way to organize this thing is using subroutines or using coroutines. And the idea now is that all the events come to the kernel as they do here also. Except in this case, what was happening was that when an event came, then the kernel said, this thread was waiting for you. And then it will go and activate that thread. Here, we will say, which function handles that event? And then we just call that function, we call it a handler. And then that function will run, exit, and then the kernel will say, what's the next event? And meanwhile, when the events are arriving, like for example on Pensano, inside the kernel there is some sort of a queue. So there's some sort of an event queue. So so interrupt service routines and all deposit entries into this event queue, and the kernel all it does is it says while true e equal to next event from queue call handler corresponding to e, and then keep repeating this process. Okay, so in this case, our handlers are nothing but functions, and they at any given point in time, I'm only in one of these handlers. I can get away with a single state. The handlers don't have to. You don't need to remember where in the handlers you were. They always enter and exit fully. So this is a very common way of structuring things. A lot simpler to implement, but the complication that here comes is that handlers can get called in any order, depending upon the order in which the events are running. So if we have to pass information back and forth from between these handlers, the programming style can become a little bit tricky. Whereas here, like my LED blinking example, I can write different things with just different threads. So it's easier to think about, arguably, but this is easier to implement because I don't even need an OS. My OS itself is a very simple thing. Okay? No context switching. So you can imagine that having some sort of priority. So your queue is maybe you can have multiple queues or you can have a priority queue. This is not preemptive. So you're raising an excellent point. These handlers are non-preemptive. That is, once I call a handler, I have to let it finish. Okay, and therefore, this style of programming has a disadvantage that if I have something which arrives while I'm in the middle of a handler, I have to wait until the middle. We'll go into some of these examples shortly, but so So the negative out here is, so this is easy to implement, memory efficient, so single stack, but hard to meet timing. Okay. So, and coroutines are kind of in the same thing. It's just that they give me the ability that the next time I go into the handler, I can go in the middle. So the handler can remember stuff.
So this is not right. These values have to
Correct. So it's non-preemptive. In either case, I have illusion of concurrency.
but if you have like a multiprocessor,
If I had a, you're right. If you had a multiprocessor, in this case, I can have these threads running. Okay. Here also, you could imagine under certain conditions, while one processor is handling one handler, I can start the next one as long as there is no dependency.
But are there any cases where, like, I mean, generally it's a simple implementation, but there are other cases where one handler like writes to a lot, right?
Yeah. So communication among handlers is much messes things up tremendously. Okay. And also remember, I said handlers always start at the beginning and end at the end, which means that if they need to remember anything, that needs to be handled specially also. Whereas here, you remember because of where you are in the program. Okay, so it's automatically remembered for you. So these are just two very different ways of doing things. This is kind of closer to the hardware, so to say. The event one and the thread one is giving you this comfort of decomposing independent things, and also many people, I think particularly those coming from software side, find threads easier to work with. Those coming from the hardware side find this easier to work with because this is closer to the picture of what happens. The hardware. But both are equally valid, and in fact, there are papers along the lines of threads are great, events are evil, and vice versa. I mean, and I kid you not, I mean, these are sort of, they are serious academic papers sort of debating the merits of these two, and I think at some level it's sort of a bit of a religious war because engineering is always about trade-offs. In this case, there are abundant trade-offs. You'll find this kind of style of programming, events, handlers, a lot, even at high-level software. Anyone done like GUI programming, for example? Let's often just say mouse click, a handler gets fired, right? Fallbacks, we call it. You have network programming like network packet arrives, you have a handler for it. So this style of programming is also very common. And in operating systems like Linux and all, there are special function calls for it. So for example, in Linux, there is something called poll, and in standard Unix, there is something called select. And what you do is you give them a list of event sources. And then what it does is, so you say while poll and pass to it a list of event sources, and then when poll returns after some time, it will tell you which event occurred, and then you process it, and then you go back to it. Okay, so Linux and OS X and Windows, while they certainly support threads, they also support this. Okay, and in case of some things like embed, this is actually extremely natural. If you think about it, ISR, interrupt service routines, is nothing but the stuff, right? I mean, except the kernel in this case is the interrupt controller in hardware. It is waiting for events to occur at different pins, and when the events occur at various pins, it calls the corresponding ISR. Okay, and so the whole interrupt service routine structure is nothing but event handling deep at the hardware level.
So if you have multiple processors, you can make it behave if like one processor handles one event and the other processor handles the other event.
And you can have multiple event queues.
Okay, and then you virtually make it look it like multi-threading as well.
You could, yes, indeed. You could think of because you can basically have multiple processors and each one of them are doing things. So right there, the moment you have multiple CPUs, you right there have true concurrency. Okay. In our case, on Hexaware, for example, there are two processors, but we can't program the other one ourselves, or at least not through embed. So that's not an option. Okay, so I've already discussed much of these. Multi-threaded sequential code flows is easier to think about. Like within a thread, I know things are operated in a certain manner. Can preempt a thread, so that goes to Nitya's point that if I am in the middle of a thread, if something more urgent occurs, I can bump out of it. Okay. So it's suitable for long running computation, because I can interrupt the computation. Cons, switching back and forth between threads means that I have to save state and all, so that's called context switching, and that can be pretty time consuming. Threads can interfere with each other, because when they talk to each other, maybe they're sharing some resource, like let's say both of them are trying to talk to the radio. So while one guy has started using the other radio, the second thread has to kind of wait for it. So it may need some ways to help mediate that access, some sort of blocking mechanism. And then also each thread needs its own stack, and therefore it's memory consuming. Events, on the other hand, organizing software as event handlers, they are just function calls, so they are super efficient to implement, very memory efficient, single stack. Basically, no context switching overhead, because function calls is one thing that processors are designed to support efficiently, because we do so many of them. No need for locking mechanism, because I'm only at one place at one point in time. Code is more compact. Cons, no preemption. So if I am in the midst of a long running computation and some urgent event comes, I'll have to wait. Code flow is somewhat unstructured, because I cannot think linearly about a single thing. I'll have to, like if I have a long running computation, I may have to break it up into pieces, and they may occur at different points in time. So it's not suitable for long running computation. And you might say, hey, I mean, we don't do long running computation. A lot of signal processing stuff and machine learning and things like that are. For example, cryptographic functions, machine learning functions. These are all things where my amount of data may be very tiny, but I may have to do a computation over a long time. For example, very common is I'll collect, I'm sampling, reading from a sensor. Let's say I'm reading from a sensor every 1 millisecond. And I'm going to collect a 10 seconds worth of sample, let's say, or whatever, 1 second worth of sample, 1,000 samples I'm going to collect. And then I'm going to do some heavy computation on it. Like I'm going to recognize what event happened. And that thing may take itself another second. But while that thing is taking second, I still have to keep sampling the sensor. So I have this long running computation, which if I were to do with the event handling way, I have to be careful, because if I hog the CPU for that entire second, then who's going to do the sampling? Now, one answer is maybe the sampling can be done by the ISR. In some cases, you can, but not always. So generally speaking, here you have this issue that long-running computations can be very problematic to work with. Okay, so I think I'm at a good transition point right now. So let's do a quick 5-minute break, and then we'll pick up this again.
All of the acceleration the link you've given us for microelectronic, I think, and apparently they're having an issue and they can ship it only on Monday, next Monday. Is that going to be okay with the assignment?
Yeah, you
or
can
shall
kind
I
of.
cancel the order?
I think at this Monday.
Next Monday is when they can ship it. Apparently they're missing some
You
parts.
can order from Mouser.
Okay.
Yeah, that's a lot quicker.
And no, I think DigiKey took a week as well.
DigiKey took a week also. Mouser, I mean, when I ordered for myself, Mouser came in a couple of days.
Okay.
Yeah.
So I'll see the estimated delivery time, and depending on that, cancel that order and place an order.
Yeah, or otherwise until then. I've never ordered from that company,
It comes from Serbia or somewhere.
Yeah, it's a European thing. That's why I never ordered it.
I didn't realize that.
Yeah, so Mouser is kind of the easier way to do it.
Okay.
Just the academic piece.
Yeah, I saw it.
And can I borrow one
From you can, yeah.
because I just ordered and
Okay. Nitya, I mean, if you want, you can also borrow one from me, and yeah, that's an option too. You can come with like a podcast.
So on Piazza, we put up the assignments, or not assignments, the lectures.
Mhm.
They're not the annotated formats. Have you ever put the annotated ones?
Yeah, I have not. What I'll do is I'll put the folder on which everything is
Uh-huh.
located so that you guys can just check for
Oh,
yourself.
okay,
there.
okay.
Yeah, I'll do that. Thanks for. Yeah.
And the second question, so for event handlers, right, they don't necessarily have to be asynchronous, right?
What do you mean by?
Where you can call an event handler and then continue on with the rest of your
You
code.
can't because it's a function call. So
Yeah,
when you
so-
call it, you are stuck there.
Yeah, okay, okay.
Yeah.
But could you implement
The only thing that can happen while the interrupt handler is running is it interrupts.
Uh-huh.
Okay, and whatever
Yeah.
interrupts can do.
Okay.
So ISRs can do.
Yeah, yeah. But could you kind of enable a asynchronous type event handler by using threads then? Like
Yeah,
finding a
I mean
thread
you
and then-
could realize then they will not be handlers. Okay, I mean
Uh-huh.
you can say that I'm sending a message to a thread, but then
Yeah.
it's really threaded program.
Okay.
You can use threads like handler,
Yeah.
kind of a more powerful handlers, but
Mhm.
it would still be threads.
Okay.
Okay, so let's restart. Um, so one point that came up during the break is these handlers are just function calls. So while you enter them, there's nothing else you can do other than that ISRs can still happen. So if there is some hardware interrupt, then behind the scene, the handler may be instructed to run the ISR, one or more ISRs, but unless the handler chooses to disable, right? So that may still happen, and those ISRs in turn may put an event into the queue for the event queue to run. Now, having said all of this, I mean, handlers and threads are kind of two ways of eventually doing the same thing, right? At the end of the day, these are just different ways of organizing the software. I can certainly use threads like event handlers, and inside a thread, I can write my own event handling loop, like I described using the poll or select in case of Linux, right? So, yeah, I don't know where it was. Yeah, poll and select. So oftentimes these two worlds collide in complicated ways, but deep down, if you think about it, I mean, this view is a little bit like if you are seeing finite state machines in your digital logic course or any software course. It's a bit like that. I am in the state. The state corresponds to a memory associated with these handlers, and events cause me to execute a state function and move from one state to another. At any given point in time, I'm in a single state and then this does exactly one thing in a finite state machine. Threads are multiple machines running in that function.
So handlers can either be both user defined and OS defined.
OSs which provide this, what they give you is abstraction that you can attach callbacks, as they call it, or functions, to different types of events. So the OS will define a type of event, like they may have an event for character byte arrival on UR, and you can attach a function.
You have standard defined.
Yeah. In fact, you would see in TinyVerse here says introduction to Contiki. So Contiki is an embedded OS which is pretty popular, particularly in Europe. And what Contiki does is it actually provides both. It provides this abstraction and it also provides a threaded abstraction, and you can kind of have your pick. We are not using it because it's not supported on most of the platforms that we're after, and also mbed can also be used in the same manner. Okay, so I think many operating systems kind of provide both in some way. So what all of this then leads to is three very common ways of organizing software in embedded systems. So one is a single task, kind of like the simplest program you can imagine in embed. That is, you write a main function, and within the main function, usually you will have a while loop, because one thing that characterizes embedded system is that they kind of never exit, so to say, right? I mean, they're just sitting and running events. So the very common structure for single task is do some setup and then go into an infinite loop. In fact, those of you who have done Arduino programming, you would see that Arduino forces you to write these two functions, a setup function and a loop function, okay, because it follows this kind of single task programming model. Okay. Well, not quite. So it's closer to this one, but I'll come. So foreground, background task is a second model. It basically says I'm going to think of my system as two tasks: a task running in the background all the time, and a second task which, whenever it's ready to run, preempts the background task, runs, goes out. And then finally, multitasking, the way kind of we are doing this. So let's take an example. Let's say you are writing some sort of a controller for something, let's say a building automation system or something like that. So what's happening is there is a clock tick which comes every 20 milliseconds. So I have a system tick, clock tick of some sort. And then every time this clock tick comes, I first need to run some function. We call it clock module. It needs to run on every clock tick. Then there is another function which is some sort of a control module. And it needs to run every 40 milliseconds, every alternate clock tick. And then I have three other functions which do not have any kind of a tight timing constraint. They're kind of soft. As long as they happen reasonably quickly, I'm good. So there is some sort of a display update for the operator. There's some screen in which data is being displayed, some sort of operator input. So the operator is feeding inputs, and then finally kind of logging some information for management purposes. Okay? Very typical. In fact, a lot of embedded systems, network embedded systems get used in factories, and they are called as programmable logic controllers, PLCs. So this is very typical of which stands for programmable logic controllers. These are special embedded computers which are widely used in factories, ships, whatever, big industrial stuff, okay? Electrical grid, water plants, stuff like that. And what they do is, I mean, they're robust, simple computers, very much like our embeds, and they basically sit in a cycle. They have a clock tick. Every clock tick, at the beginning, they read sensors, do their stuff, write the actuator values, repeat the process forever. So these kind of things that we see are very commonly encountered there, right? I mean, some relays need to be handled every clock tick. Some other tasks need to be done at a different way. So we have this example. So let's see how we might structure it in each one of these three different ways of software. So if I were to take a single task approach, I might write it this way. I could say while true, wait for the clock tick, and then when the clock tick comes, I do a clock module. I make a function called a clock module. And then what I do is I can have, this is just one way, I can have this if then else, where first I check, is it time for control? I could do it by maintaining some sort of a Boolean variable which I toggle through every loop. This is not a complete code. So if it's time for control, do a control module. Otherwise, if it is time for display update, we do the display module. Time for operator input, go and check the operator input. And then if it's time for management, do the management stuff. So if you think about it, let's say that these various modules took time T1, T2, T3, T4, and T5, these 5 functions. And basically what we are saying is that T1 plus, so this constraint must be satisfied, right? T1 plus the maximum through this if then else clause must be less than equal to 20 milliseconds because I have to go back into the next iteration in time to handle get the next clock. Okay. Now, if you think about it, this is very constraining because what if T2, T3, T4, these things, T3, T4, T5 are pretty time consuming. So let's say my clock module, for the sake of argument, let's say the clock module is 10 milliseconds. Okay. Now, if you think about it, with this model, since T2 needs to be handled only every alternate clock cycle, so T2 actually can be more than the remaining time, more than 10 milliseconds, if I'm willing to split. But that will complicate the job of this function quite a bit, right? So this is where I start running into that if T2, T3, T4, T5 are actually greater than 10, but averaged on an average they are less than 10. But any given call may take more than 10, then I will violate this timing constraint. So this kind of a single loop becomes very problematic when you have these kind of interacting timing constraints going on or long running computation. So it may require you to split these functions. Now that can be a problem because splitting a function so that each part has some timing characteristic is often not easy because the function may have a loop inside it. Where do you chop it? What if it's data dependent? All these kind of questions come up, and so fundamentally this kind of an approach gets very complicated because what if I have to start breaking up subroutine calls and say part 1, part 2, part 3 of a subroutine call, things just get very messy very rapidly. We saw a little bit of that when I introduced that example of two LEDs, right? Where if that was a different kind of thing where things were not nice, if the periods were not nice multiples of each other, then we had a problem. So next approach, foreground background, makes use of the fact that in the form of interrupts, processors, every processor almost, gives you two tasks, a two-tasking system, right? Because whatever I may be doing, if the interrupt comes, it's kind of like a second task. The interrupt service routine is a task running in parallel. It can always preempt. So you can think of ISR as a high priority task which will always preempt the normal user code. So I can make use of that and I can say on interrupt, do the clock module. So this is my ISR. That's a foreground. That's a high priority thing. So inside the interrupt handler, what you do is you always do the clock module, and alternate interrupt handlers, I will also do the control module. Okay. Now, and then my background, this is kind of like my main program. What I'll do is I'll have a for loop in which I'm going to do those display and operation and management functions in the background. So what will happen is that time critical stuff I have relegated to the ISR, and it will always interrupt this long, potentially long running background. And this way of separating the two out immediately has an advantage because the only thing I need to now worry about is T1 plus T2 should be less than 20 milliseconds, or with some leftover, right? Okay, so let's say we give a little bit of a share for this, but as long as T1 plus T2 plus some epsilon, okay, is less than 20 milliseconds, I'm good to go. So this is and this is multitasking for free because support for ISR is built into hardware, so you're not doing anything at the OS level or anything like that. It's just available to you. So in Mbed, you can write functions and declare them to the ISR, and then you can write a main function, and you can do it this way. Arduino, the same story, right? In Arduino also, you can write functions to the ISR.
I'm not sure, but if you understand that if you go into the ISR, then you're suspending the main function for the duration.
For that duration, yes. But that is why the non-time critical stuff has to go there.
So it's not really like a foreground or a background, it's just...
It is foreground background in the sense that if this thing happens, the time critical stuff, it always takes the CPU. So that's why it's called foreground. Okay? So basically now I have two tasks, one high priority foreground task and one lower priority background task. There is no such thing as true parallelism, right? So what you do have is there are processors which have multiple interrupt handlers, but only one of them will run at a time, and usually they don't allow nesting. So you can say that maybe I have multiple foreground tasks. They are like but only one of them can be running at a time. There is no special name for it. You could always think of it as a generalization of this. So Mbed, Arduino without its RTOS kind of look like this. You can program them in this manner. And for a lot of systems, you can get away with this thing, right? I mean, and if these two parts need to talk with each other, you can have a queue so that when this kind, the foreground stuff, the ISR, handles the quick and dirty time critical stuff, and then it puts the rest of the stuff in a task queue, and then the background stuff keeps pulling stuff off that task queue to process. Okay, so in my example I had cited where I wanted to process 1 second or 10-second worth of sensor data, then what the ISRs can do is ISR can put stuff into some data structure, and when enough have piled up, they can put it into a queue, and meanwhile the background task will just keep looking, is there a new entry into the queue. So the queue is being written by the ISRs and being read by the background. It's a very common paradigm, and a lot of very useful, fairly complicated systems, you can just do it this way. In fact, some of the popular operating systems in the embedded space is something called TinyOS or Berkeley, for example, are organized like that, foreground background systems. And finally, we have the multitasking. This, needless to say, is the most general and most complicated thing. So multiple tasks. In our case, there are 5 tasks, right? Control, clock, control, operator, display, management. Each task is carried out in parallel, depending upon the OS and the kind of things. I mean, sometimes you see them call as tasks, threads, processes, whatnot, but I'm usually thinking of them in the same way. Mbed calls it thread. Okay. No assumption about the number of processors. Okay, so I can have multiple tasks running on a single processor, and it's the job of the kernel, the operating system, to share the CPU among them. So tasks simultaneously, and I'm going to put this simultaneously in a quote in the sense that it is not true simultaneity because I have a single processor, but somehow since they are sharing the thing, they interact with multiple external elements simultaneously. So they can, one task will be monitoring a sensor, another one could be controlling an actuator, a third one might be monitoring I/O from the user, all quasi-parallel. Okay? So that's a very important part. It's the illusion of parallelism that they provide. What it requires is that there should be some entity, some piece of software, which is responsible for this juggling, right? Because I have a single processor. Which task should run, moreover, not just which task to run, but which task to run so that I can keep meeting my timing requirements, right? Task 1, the clock task said, I need to run every 20 milliseconds. Task 2, the control one says, I need to run every 40 milliseconds, and I need to finish before the next time is and so on and so forth. Sharing the data between concurrent tasks. Almost any system of even moderate interest, tasks would talk to each other. One task will send data to another task. It's highly unlikely that you have systems where these tasks are just isolated. So it is in this space where you pretty much have to begin to use an OS. While you could write your own, and it's actually a tremendously interesting exercise to roll your own threading system. You learn a lot about computers that way, but most people perhaps are not so inclined. So this is where you use carefully designed and properly optimized embedded operating systems. So so while you will see the word embedded OS thrown around quite liberally, and some of them are just foreground background systems, or perhaps even a single program system, really what deserves to be called an OS is when you begin to worry about stability. Okay, that's the bare minimum functionality that you would like an OS to provide. So Arduino, for example, doesn't have any of this. Arduino is foreground background. Mbed has an RTOS, but you can use Mbed also in just a simple foreground background mode. TinyOS, the other one I mentioned, Berkeley, is again foreground background. Okay, and then what they do is on top of foreground background, they provide extra goodies to make your life easier. How ISRs talk to the background task, this kind of thing. They just provide some extra abstractions to make writing software easier. But fundamentally, that's the structure. Signal program, as you might imagine, is just a special case of foreground background, and if you are not writing any ISRs, then you are doing a signal program. Okay, but if you are writing any sort of interrupt service routine, then you are doing foreground background. So let's look at embed RTOS a little bit, just to give you an example of how one operating system handles this multi-threading, multitasking case. Okay, so in embed RTOS, as you noticed, there are threads. Now, what it used to be, there used to be something called an embed RTOS as a separate entity from embed OS. But then in the newer versions that we are using, the embed OS 5.7 or 8 or whatever, they keep coming out with a new version every week almost. That whole stuff is rolled in. The actual real-time operating system is from a company called Kyle, which actually I think one of you had mentioned because they make programming tools for embedded systems. So what ARM slash embed did is that they took the Kyle RTX operating system and they wrapped it into C++ classes, and that's what they have provided as part of embed. So at this stage in embed, you have a bunch of class libraries, I was showing on that web page, which basically are a wrapper around the Kyle or key operating system. So it's really a description of that. So the main feature of this is thread, right? So that's a software module. So the way threads work, and this is a general story for at some level for any operating system of this type. A thread can be in one of several states. In this case, there are 4 states. The first is thread can be running on the CPU. Since I have only one CPU, so only one thread could be running. And if none of my threads are ready to run, then perhaps the operating system will have some sort of a default thread that will be running. Then I may have threads which are waiting for something to happen. Like for example, they are waiting for an event and that event hasn't occurred, so that thread is in a wait mode. In which case, it's in a set called waiting. It could be waiting for an event, the event should be generated by an ISR in response to some signal in a thread. Or it could be waiting for an event from a timer or from another thread or whatever, okay, the network package. So waiting. Then at some stage, that event would happen, and so now the thread can run, except the CPU is currently running something. So what the OS will do is it will mark the thread as ready to run and put it into this ready set. Okay, then at some stage, the CPU will decide that one of the ready threads, it will actually put it on the CPU. It may do it once the currently running thing finishes, or it may actually actively bump it off. Okay, either one of those options is possible. So the operating system has those rights. And finally, at some stage, the thread dies, it exits, and then it becomes inactive. The OS is kind of clean. So what you see is here is kind of like a state diagram of my overall system. That threads can be in one of these 4 states, and there are various ways of transitioning. So you enter into inactive because of termination. If you are inactive, then you can reactivate them or create them or whatnot. In this case, you may either go to running or ready. You go from waiting to ready when the event occurs. You go from running to waiting because some sort of a wait occurs, like wait 1 second, those kind of things, right? What is happening under the hood is we are telling the OS start the timer. I'm interested in the timer when time reaches its value, and then at that point in time, generate an event, and then I'll be ready to run again. When the event occurs, one of 2 possibilities: CPU was free, or maybe this really ready thread is the highest priority task, then that will get the move to running, or otherwise it will get put away. Now, how does it decide which one to actually give the CPU to whenever it's time to decide? So what this thing does is, we'll see later on, highest priority thread runs. Okay, so that's the simple rule embed follows. It's not the rule that every OS does, but embed RTOS follows this rule that threads have priorities, and at any given point in time, the highest priority thread which can run is the one which is going to be in the CPU. Okay, so if it means that a thread is running and an interrupt comes, and that interrupt generates an event, and that event causes a thread which was previously waiting to now become ready, and this thread has the highest priority, then the C operating system will bump off the currently running thread. It will move it to the ready pool, so that's why you see preemption, and put the newly ready high priority thread onto the line. And it's always doing that. Now, the reason I say that this is not what all OSs do, you have to allow for questions like, what happens if multiple threads have the same priority? Then you will do some sort of a round robin. You're going to share. Some CPUs only do the latter. Some operating systems, in the sense they don't have priorities, they only do round robin sharing. And then there are ways in which you can share in a prioritized manner. You might say threads of one type may get twice the CPU as the other type. Okay, so it's not strict priority, but it's relative importance. So there are many different ways this thing can be managed as to which thread is running. Real-time operating systems of the type that embed represents usually provide this process, that they attach a priority and they make sure that only the highest priority ready thread is the one which is running. Okay, the only thing which can interrupt this thread are the ISR. ISRs are still running, and whenever they come, they still sort of process it. It is possible, because you have full control of the hardware, that you can disable the interrupts. But if you disable the interrupts, you are doing it, you have to do it very carefully, because any interrupts that arrive during that time will be lost. Okay, so one has to be very careful about it, but you can do it, because there is nothing, unlike the standard laptops and all, there's nothing preventing you from doing anything to the hardware. Okay, so threads are the most important piece. And then there's a whole bunch of stuff supporting threads, so that they can talk with each other, so that they can do more useful stuff. But that everything else builds upon top of it. So one very common thing when you have multiple tasks is that we need to share things, right? I mean, we as individuals share resources, so we always kind of come up with a protocol, right? We come up with a protocol like, okay, you go first, then you are done, then I will do it. We kind of order ourselves, right? Because a lot of resources that we use, like sensors, radios, and all, may not allow multiple tasks to be simultaneously working with them. So to arbitrate access between them is we use something called mutex, which really is a short form for mutual exclusion. So you will see that embed provides an object called mutex, and the idea is that that mutex is kind of like a guard for a shared resource. That shared resource could be a piece of hardware. That shared resource could be a data structure in memory. Main thing is we want to make sure that while one thread is using that resource, the other thread cannot use it. Okay. Now, one way of ensuring that if this thread is using the resource, the other thread doesn't use it is what? Anyone? Any suggestion? Let's say we didn't have mutex. How would you make sure that the other thread does not get to use the resource and can't disrupt what this thread is doing? Yeah, so is there some easy way for you to ensure that do not disturb? Huh? How would that? But that depends upon nicety. We don't want about niceness, right? I mean, it has to be something that is guaranteed. The other thread should not be able to disturb it. Guaranteed, right? That's what we want. Huh? Disable interrupt, exactly. If you disable interrupts, nothing can happen. The OS can't do anything, right? The only two ways OS gets control, right? One is through the ISR. If I disable interrupt, I can't. Another is I make an API call, right? So if I don't make an API call and I disable interrupts, then OS has lost control over it, right? Which is why in systems like our laptops and all, you don't get to disable interrupts because all hell will break loose if your normal programs could do that. So alternative would have been disable interrupts. But that would be like bringing a unwieldy hammer to this problem, which will create problems all over. So you don't use this thing. So this is not a good thing to do. So we go with this mutual exclusion, which is an API call with an associated object, where the thread which wishes to use the resource is going to make a call called wait. It will say wait on that resource. And what that wait does is it basically says, I'm going to wait in the queue until it's my turn to start using the resource. And then when I'm done using the resource, I'm going to call release. And every thread does that, and the OS kind of makes sure, guarantee that only one thread will get to be using the resource. Okay? Well, I say quote guaranteed here because so it's kind of an answer. Since there are no protections here, so expect it conceivably crash the OS. But leave that aside. Okay, if the intentions are good, the OS will ensure that this protocol is followed. Okay, so that's mutual mutex. And again, if we go to here, we'll see mutex, right? In fact, as you can see, I kind of got the picture from here. So this is how we okay, so it seems like the API has changed. I'm using kind of API from the original RTOS, so they call it lock and unlock. Mutex lock and mutex unlock, and the printf is being done. So this is actually printf is a great example. What does printf do? Printf sends the string out to the terminal. If I had two threads, both of them doing printf, then the characters can get muddled up. So what we do is we want to make sure that if one thread is doing the printf, let it do the whole job. If the printf is like a shared resource now, on the terminal, on the computers, on the host side. So therefore we have a mutex for stdio, which is declared up to the top, and we do std mutex lock and unlock to kind of do the and by the way, in this particular case, I have two threads. They are just being called with different names. So it's a single function. So this is this callback type programming. I'm creating two threads. Both of them correspond to the same function, but be called with different arguments. And this function in turn is making use of this notified thing. So we have two threads, and they could intermingle with each other. So just take a look at the code on the website to see what's going on. But the basic idea is mutex is like when I start using the resource, I'm putting a lock, and when I stop using it, I put an unlock. If I call the lock and there's already someone inside the room, inside the resource, then the thread will wait out. So that's mutex. Next up, semaphore. Even more complicated. So what happens in semaphore is the following: that so mutex was like a room with a single person capability. Semaphore is like a room where n people are allowed and no more. Okay, or a resource, n things are allowed. So I can go and say I need this quantity of the resource. Okay, I need like two chairs in the room, and the room has 10 chairs. Okay, so as long as the total number of chairs requested by various threads is less than equal to 10, all of them will be let in. But if someone suddenly asks for 5 and already 7 are taken, then this 5 will have to wait until there are sufficient number of chairs left. So semaphore is an object that provides that. Again, I think the actual call may have changed now with the latest releases, but in this particular case there are 6 slots, and therefore there could be a total demand of 6 that can be met simultaneously. So as you can imagine, this is built using mutex plus some sort of a shared data structure to make this magic happen. But again, mbed provides this for you to use. Signals are a way for things to talk to each other. So one thread can send an event to another thread. Hmm? That is, yeah. Yeah. The jargon is often very used differently. So the way these guys are using it in this way, many places there is no separate thing called mutex. Binary semaphore is a mutex. Okay, so what Nitya is saying is that mutex is nothing but a semaphore with a solution. But implementation wise, they first make a mutex, and usually there is some hardware support possibly for mutexes, and then you build everything else on top of that. Okay, signals are ways for sending messages from one thread to another. An event, like one thread is saying something happened. So I didn't have a nice picture out here, but there are 2 calls out here. There is a set call out here. So what you do is you basically set a signal, and then the other side can wait on the signal. Okay, so essentially I'm kind of sending an event, raising the flag, and the other side can wait for the flag to be raised. So signals, and then on top of signals are built signals and mutex are built queues, where the idea is I can send messages, not simply a binary event, but really kind of entire data structures. So I may have a message in one thread, or in service routine, they put an object into a queue, and the other side may wait for that object. If the queue is empty, this guy will wait. If the queue has something in it, it will immediately get the value. And again, the OS takes care of that. If you try to put something out here, I'll just come to you in a moment. If I try to put something, if the queue is full, then you will wait on it. But one very important thing, ISR can never wait. Any operation which directly or indirectly will result in the ISR getting blocked. Remember, ISR is not like a true thread, right? It's a hardware enforcement. So it can't go into a wait state. So it is not allowed to do anything which can potentially result in a wait, and that includes no printf. Signals are like software interrupts. So it's between 2 software entities. Interrupt is always kind of from some hardware source. So yeah, that's a good analogy. So let me just write it down. Or kind of. Okay, there are some differences. So you're talking about in Linux and all? Yeah. Yeah, so what she's referring to is if you look at programming in Linux and all, there is concept of signal and signal handlers. You can write signal handlers kind of in the same way. So I don't know about this particular one, but I think usually what they do is the queue is a queue of pointers to objects, and it is usually typed. So there's a queue of a message of certain type because we're dealing with it. But there are other ways of kind of doing it. You could have arbitrary length, byte blocks or whatnot. But I think in case of embed, it is certain complex. Okay, so queue. So as you can see that you can do a lot of stuff. There's something called mail, which is queue together with signals. Okay, and then finally there are timers, RTOS timers. Now this timer actually has been deprecated. Deprecated means obsolete. Okay, so while Embed still provides it, they discourage you from using it because the same functionality can be provided by queues and signals. So basically, in case of timers, the idea is that you start a timer with a particular value, and when the timer fires, a callback function is called. Okay, so you could work it this way, and while the timer is running, you can restart it again in the middle. So there are some very common timers which are used in software. So like one timer that embedded systems use quite a bit is called watchdog timer. And the idea behind watchdog timer is that what if the system hangs? Something bad has happened, the software is hung. So watchdog timer is a special timer which, if it fires, it will reset the system. So the idea is that to show that the software is not hung, you are supposed to go and restart the timer before it fires. Okay, so we will say watchdog timer with a 10-second firing time, and then if my and I have to make sure in software that my task goes and resets the timer, and if it fails to, then it will be viewed as if my system is hung and the whole thing is reset again. So it's kind of like a safety guard. Usually processors provide a watchdog timer which is outside the control of the OS. So it says that no one can stop it. Sorry. If no one can disable it, okay, you can restart it. Anyway, so that's the timer, and there are there's a whole API with interrupt service routines, and a big caveat: you cannot use anything in an ISR where you have to wait, and that includes mutex, because if an ISR were to call mutex, then it may have to wait because someone else may have grabbed it. So ISRs are distinct from functions in the second manner also. That is, there are things that you just can't do inside an ISR. So we're going to pick this thing up on Thursday. What I do urge you is to go and read this part of Embed OS to familiarize how concurrency and all is managed. It's actually pretty interesting thing because this gives you an exposure of what's happening into computers at the low level. But it's, on the other hand, it's just these basic concepts, and once you get the grasp of it, you can do all sort of concurrency management. Okay, so see you guys on Thursday, and again, I'm holding office hours right now, and also office hours tomorrow as well.